Good. Then we come to a mean shift. It's one instance of a clustering algorithm. And so cluster analysis is still part of this unsupervised learning. And in cluster analysis, what we do is we find groupings in data or sometimes we can summarize these groups in terms of prototypes. By prototypes or representatives. And there is a great choice of clustering algorithms, including so-called flat clusterings or hierarchical clusterings, where the groupings are nested. And there is crisp and fuzzy clustering. Crisp clustering means observations are assigned to one cluster or to the other. Fuzzy clusterings means they can be, for example, 80% this cluster, 20% that cluster. And usually in cluster algorithms, you need to specify one of two things, namely you always need to tell it what's the granularity of clusters that you look for. So requires what? Requires, okay, I'll be more concrete. So this granularity, you can adjust either by specifying the number of clusters. So the very famous example for this would be k-means clustering, where you set a parameter k. If you set it to 20, that means you're going to find 20 clusters. Or what you need is a scale or bandwidth. What's the scale of a cluster, or what's the bandwidth in a kernel that you're using? And my favorite example for why these are needed is if somebody asks you to cluster the universe, there are just many valid answers. So you could say there are agglomerations of galaxies which are one cluster, or you could say one galaxy is a cluster, or you could say each solar system is a cluster, or you could say each planet is a cluster, or from the planets we have to go down quite a bit. We have to go down to molecules or to atoms. These are also meaningful clusters, and then to elementary particles. And you know, it's if I just ask you to cluster the universe, it's not clear if solar systems is a better answer or if galaxies are a better answer. And by specifying a length scale, a characteristic scale, you can specify what you mean. Or depending on how you choose it, you will get those different answers. All right, and now this was cluster analysis in general, and mean shift in particular. Is closely associated with the kernel density estimation. Namely, mean shift performs a gradient ascent on a kernel density estimate. And this, what does it do? It finds the modes or the peaks in the density, and it also clusters your observations. So I'm giving a 2D example. And I'm now inventing a cluster here, and I'm inventing another cluster there. I'm trying to copy the data. So these are now observations in a 2D space. And I can now do kernel density estimation with 2 different bandwidths. If I use an appropriate bandwidth, then I would find some local maximum here. You know, those are the ISO contour lines. My kernel density estimate might look something like so. And if I choose a much, much bigger kernel, then, well, I will obtain something. If I use a huge kernel, it will obscure the actual shape of the cluster. Yeah? Might look, you know, like if I use, let's say, a very wide Gaussian, then I will obtain something which looks a little bit like a distorted Gaussian. All right, and what we can now do is we can, from each observation, from each and every observation, we can just start and do a gradient ascent. Yeah? So we just walk uphill along the kernel density estimate. And well, in this case, we have a single mode, so a single maximum. And that means all points will walk. That's a pretty boring clustering, yeah, but all points will walk here to the same center. Here the situation is different. Here points will walk. So these points will walk to this center, and those points will walk to that center. Okay, and these trajectories here, they look pretty straight, but in principle they can be curved also depending on the precise shape. So this is what's meant by gradient ascent, and then afterwards I still need some post-processing to find, you know, all the points that ended up in the same maximum. But what I like about the mean shift algorithm is that it is, you know, well understood what it does, because it operates on this underlying kernel density estimate. And also what I like is that I don't need to specify the number of clusters. I think it's quite versatile to be able to specify only the length scale. All right, and what does this do in formula? So this gradient ascent we can write as follows. We have some sample j, and we find its coordinate at time t+1. And this we obtain by taking the coordinate in the previous time, step t, and then doing a bit of gradient ascent. So this is a parameter to choose the step size. And then we need the gradient. This gradient is evaluated at that point's location at time t, and with the when we differentiate with respect to a vector, there are 2 conventions. There's a column layout or row layout. I'm using column layout, so I need to transpose here. All right, and now this density estimate here, we can use the kernel density estimate, and so just inserting the formula for the kernel density estimate, I need the derivative of my kernel. And I'm omitting here the parameter specifying its bandwidth. And we can do this concretely for the Epanechnikov kernel. So the Epanechnikov kernel, again, in one dimension, is this truncated parabola. So it's parabola and then truncated to 0. And here for this example of the Epanechnikov the Epanechnikov kernel itself is 1 minus here x minus xi squared, or I'm writing x minus xi transpose times x minus xi. I'm sorry, I'm running out of space here. It is this inside this range here. I'm now simply assuming that the bandwidth here is 1. And it is 0 otherwise. Okay, now we can differentiate this thing. Yeah, so for the case of the Epanechnikov, a little bit bigger. I'll try. So if I differentiate the 1, nothing happens, and from the other terms, I get 2, I get minus 2 x transpose. This transpose is from, again, the column layout of the derivative that I'm using here. And it will be minus that plus 2 xi transpose. And all right. And this formula we can now use to find an update. So my xj t plus 1 is going to be xjt plus alpha. And now we do this for this case of the Epanechnikov kernel. So it will be one over n, and then we sum only for those over those points that are close enough. So we sum over the points I, which have a distance that is sufficiently small. Xi minus xj should be smaller than 1. And then we need the actual derivative here, which was twice. I'm absorbing, or I'm changing these two terms around here. Xit minus xt. Good. And let's see, the transpose is not right. I had one transpose up there, and I had another transpose here, and they cancel. And so this was wrong. I'm sorry. Good. Okay, so this would tell me how to walk up the hill. Yeah, I do one step, and then do another step, and so on. And that's okay. but it's not going to converge very fast. Yeah? In particular, our kernel density estimate, if it's a sum of Epanechnikov kernels, so it's a sum of these truncated parabolae, you know, it might look something like so. And we now try and do a gradient ascent. And as we are close to the local maximum, the gradient is going to get really, really small. Yeah? So it would take a long time. Now we could do, you know, things like line search and so on. But we can also pretend that we have a Newton second order problem defined by the points that we see in the vicinity of our current point J. And then we move directly to the head or to the maximum of the parabola that we see locally. Yeah? So in other words, the mean shift move that one can use in practice looks as follows: xj t plus 1 equals, and now we just move to the center of mass. So we sum over all points I which are close enough. Over their locations. And then we count how many points were in this vicinity. Okay, so what we have, what this thing is, it's the local center of mass. By local, I mean that we only consider the points which are close by, and normally we weight them. But for the case of the Epanechnikov kernel, this weight is just uniform. And that defines a shadow kernel that's not the general technical term in machine learning. It's just the name which the single author of this paper used in his publication describing the invention of this mean shift algorithm. And so effectively, the Epanechnikov kernel is associated with this shadow kernel, which just asks what points are within a distance of +1. And once we have updated the coordinate here, this set of neighbors can change, and so it still is an iterative algorithm. Yeah, it still will not generally converge in a single step, but it does so reasonably fast. So, couple of comments. This mean shift algorithm or mean shift clustering is a gradient ascent on an underlying kernel density estimate. And here we could choose some other function. We could choose some function that depends on xi minus xj. And we could add this function down here. And if we do so, we can pick other kernels than this one here, like we can pick something smoother, for example. And then this will correspond to gradient ascents on kernel density estimates with a different kernel.
Shouldn't the x be xjt because you're evaluating the derivative of this one?
So the xi here is correct, and this one, it should be xj, I think. The xi minus x. That's correct. Thank you. And then you said something about what? No, that disappeared because I had a transpose up here, and then I had a second transpose there, and then they cancel. Ah, the index, I'm sorry. You are right. So the xj is the xjt, the small t, yes. Thank you. Any more errors? Okay. Thanks for finding that. So different shadow kernels imply different KDE kernels. What's nice is that we need to specify only the scale by choosing the width of the kernel. We don't need to specify the number of clusters. This is good. But on the other hand, it struggles with elongated clusters. I'm writing here, it struggles with long clusters. So if you have a cluster which is, I'm drawing equi-contour lines here, which is, sort of flat. What the gradient ascent for meaningful bandwidth will give you is that it finds a different local maxima here. Yeah, so also if we do a kernel density estimate here, we will find weak local maxima, and I would like to think of this here as a single cluster, but what we will find in fact are local maxima. That's what I mean here when I say it struggles with long clusters. Also, like kernel density estimate, it can be quite slow, but overall I find this to be an elegant algorithm, and this is described in a single author paper by Yizong Cheng. Which has something mean shift in the title. And I like the paper a lot because the mean shift algorithm as such, so this formula, this was invented before. This formula had been around since the 70s, but then it took 20 years for somebody to understand the relation to the kernel density estimate and to describe that relation in detail with these shadow kernels and so on. And that's what Yizong Cheng did in this paper here. All right, very good. So much for our first foray into unsupervised learning. And on Thursday, we will finally go supervised by starting to talk about regression. Thank you very much.